Greetings. In this video, we will be talking about the comparison test regarding infinite series. So let's take some concrete example. The example could be 1 to infinity, which I mean n equals 1, but shorthand notation. And so 1 to infinity of the argument, let's say the argument being 1 over 5n minus 3. Now, the point here is that we want to see, does it converge, does it diverge? And the answer to this, in this case, is possible to generate through knowing the comparison test. And the comparison test, what it talks about are series that have positive terms only and series that we can compare to another series. So for comparison test, we're always considering two series, and one of them will be the one that we're looking for, whether it's with converges or diverges, and the other one we will, and the next and the second one of the two will be some that we think of to compare it to. Either that one we want to be bigger or smaller, depending on the context within the rules that I'm going to state in a second. So the point here is that we have two infinite series. Let's say the first one is an, second one is bn. What I mean is, I'm not writing the bounds, although I mean 1 to infinity for this case, for example, for both. The same bounds for both. They're both starting from some finite value going to infinity. And so, the point here is that we want both of them to be positive for all terms, or at least 0, not negative for any of their terms. That's the first condition. So they must most of the series will have to bound it. So the sequences behind the series, the terms, all of the terms must be bounded by 0 from below, and also therefore the series, when we add all these terms, that will be bounded by 0, y equals 0, or in other words the x-axis from below as well. And another property is we have bn that is bigger or equal at least to an. So what I'm saying is we have two sequences, they're both positive, both two series with terms that are positive. The corresponding terms are in such a way that for each two corresponding terms, from bn and an respectively, we have bn is bigger than an. So for the same n, bn is bigger than an. Any term, any corresponding term, will be larger in the case of the bn infinite series. And so with this logic, we can have a lot of results and find out a lot of things, because we can look for some simpler series. So we have this one, and it's basically some other series that we already know or might know more probably, and we will compare it to that. And we also know that some results regarding the comparisons will directly lead us to determining convergence versus divergence. And that's the point. We want to find out, does it diverge, does it converge, by comparing it to some simpler series. So in this case, what simpler series do we have? We have, this is 1 over 5n minus 3. A simpler series I would think of is 1 over 5n. And why do I want to think of? Well, I think that 5n minus 3 in the denominator makes smaller, makes basically actually smaller the denominator itself, but bigger the whole value of this each term. And so this should be bigger or equal to 1 over 5n. For example, for n, the smallest n equals 1, and it should apply for all n. It must apply for all n equals 1, it will be 1 over 5 minus 3, 1 over 2, and this one will be 1 over 5. So this one is smaller than this one for 2 as well. 1 over 7 is bigger than 1 over 10. And so I have found another simpler argument for series that I could also talk about, such that for each n, 1 and higher, up until as high of an n we want, because it goes to infinitely large whole integer n, positive value, as the very last term, hypothetical thought in that context. In that context, I know that for all such n's, 1 over 5n is always smaller than 1 over 5n minus 3. That means if I have a sequence with the same bounds, we must consider the same bounds to be very clear about this, that has not 1 over 5n minus 3 but 1 over 5n, then it must be smaller or equal to at least to this one, to the original one. So what I'm saying is that 1 over 5n is smaller for every single term. And therefore, of course, when every single of the terms for any, in this case, actually what it corresponds is, in the case that this new one is the an, is the small one, and bn is the larger one. So the original one is the bn, and the new one we thought of is the an. And in that context, we can now draw some conclusions. So, a point that I made some time ago is that if one of the series diverges, and it is the smaller one, then the bigger one, which has a higher value for every corresponding term, will also diverge, because it's adding up all the terms. And if every term is bigger than it, if that smaller one, if that one that has every term at least the same or smaller, then this bigger one will, of course, diverge as well. So what we found actually in this case is exactly that. We found a smaller series with an argument such that every term is smaller, even though it's just by a little bit. It's never bigger, it's always smaller. So for that reason, we can prove that this will diverge as long as this diverges. So how do we do that? Well, actually, we've gotten very close to a very common series that is known to diverge as follows. 1 to infinity, and I can take out the constant 1 over 5. I have 1 over n. And 1 over n is called the harmonic series, and it's well known to diverge. So, if a divergent series multiplied by some constant, finite constant, it still diverges. So this diverges. And therefore, this, when it's bigger for each term, well, it's bounded by below by the value of this diverging one, and it's even bigger. And this one is already diverging, so this one has to also diverge. Therefore, this one will diverge also. So the conclusion we can draw from it is that this one diverges, and we did using this comparison test. And now it can also go the other way. So we talked about two sequences that are, one is small, one is bigger, both are positive. Both never cross down below the x-axis. And one of them is always bigger than the other for every term. Now, this can also go the other way. Here we had that the small one diverges, so the big one, of course, will also diverge even more from a hypothetical standpoint, from an abstract idea, which, of course, if one diverges, there's no way to really compare which one diverges more. It will just be said that both diverge. That's the common conclusion. But in any case, we can also take it the other way. We can know that if the bigger one converges, then the smaller one will converge definitely also. So if the small one diverges, the big one must diverge, because it's even bigger. But from the other standpoint, from the opposite direction, it can be drawn as a conclusion that if one converges, the smaller one, if Bn is the converging one, where Bn is the bigger one, and An must converge. So let's look at that idea. So example of that could be this. 1 over En plus n. So, again, we can compare it to another sequence, to a different term. So, to a different argument. So we have this argument 1 over En plus n. And I suppose that it converges. And the reason is because we have this exponential term in the denominator, which makes it very big in value. And then we have this n added to it also. This would always be positive for 1 and higher, which is what we are considering. And so we know that this is always, because there is a larger value in the denominator than in the case of this new one I can think of, which is e to the n in the denominator only without the n. We can say because there's this n, but this will be always positive. This one will be always smaller than this one, at least equal, but never bigger. This one will never be bigger than this one. And so I could draw this conclusion, this first conclusion, and this was our initial series. So I can draw a new series, which is 1 over e to the n. And it will be bigger. And now if we see that this bigger one converges, then the smaller one, which is at the same time always bounded by being, and by the way, yes, this has to be always checked. This is a very important point. We always suppose we can do this for series that are bounded below by an x-axis. So all terms have to be above 0 or at least 0. We cannot have some minus terms there. It would not work necessarily. It would not necessarily imply such results. So in this case, again, it works. Why? Because we have 1 and higher, and this is always positive. So this whole thing will always be positive, all terms of this series. And now again, let's come back to where we got. This is bigger. So if this will converge, then the small one bounded by this thing from below and bounded by this one from above must converge also. Well, because this one goes to a positive finite value lower than infinity but higher than 0. Or let's say between 0, from 0 till some finite value that is not infinity. And so, what is the convergence of this one? Let's see if it converges. Well, it actually does. The reason is that this is a geometric sequence inside it. It's a geometric series. And what it means is basically it's the powers of some number, and this one is between 0 and 1. Strictly between 0 and 1, which is something that works for the geometric series, and there's a formula to even get the concrete conversion value for it. And that is as follows: 1 over 1 minus what is below the exponent n here. But actually we have to take one thing into account here and be careful about it, because one cannot use the geometric formula in the way that the geometric formula works this way, but when there is a 1 here, there must be a minus 1 here. If there is n here, there must be 0 here. So what we can do is actually we can do a 0, so we can do it from 0, but then we have to subtract the 0 term. That's just a side note, and it's not a main thing concerning this comparison test. So let's do it from 0, because the rule is to have a direct explicit formula for the value of the geometric series. Yes, we can use directly this number. Let's put the n equals 0, 1, 2, 3, and so on. But it has to go from the 0 in the case that it's just n. If it was to be 1, it has to be n minus 1. So what I'll do is, I'll do it from 0, which will generate an additional term, and then I'll subtract it. This will make one additional term, and the additional term will be 0 here. 1 over e to the 0 is 1, so I will then have to subtract the 1. But what I was talking about previously is the formula for the geometric series, which is 1 over 1 minus what this is, as follows. And so this will be our conversion value for it. So now we actually saw that this bigger sequence than the initial one is convergent. So already we can conclude this is convergent. So this is the other direction in which we can use this theorem, this test. And now just to wrap it up, we can actually evaluate the concrete value of this, which will be, well, we can do e minus 1 over e, all that 1 over e minus 1 over e minus 1, which will be e over e minus 1 minus 1. And now we can again rewrite it somehow, which will be e minus 1 over e minus 1 here. Well, this could be rewritten as e minus e plus 1 over e minus 1, which is 1 over e minus 1. So this will be the actual concrete conversion value of it. But in any case, we found out that this one is convergent.